Our today's topic is buoyancy and stability. I'm going to first take a look at an overview of our discussion. Then I'm going to introduce you to lecture objectives, and we take it from there by solving a few problems and make sure we master the topic of buoyancy and stability as it relates to our discussion. So every time an object is floating in a fluid, or when it is partially or completely submerged in a fluid, it is subjected to a force called a buoyant force. What is a buoyant force? A buoyant force is a force that has a tendency to push the object upward and prevent it from completely or partially submerging. So buoyancy is a tendency of a fluid to exert a supporting force on a body placed in the fluid. We are also going to touch base on stability, and I have a separate lecture on stability of floating and particularly stability of submerged bodies that I'm going to go over. So here I will discuss the fundamental principles of both buoyancy and stability to help you develop the ability to analyze and design devices that will operate in certain environment, as we will see. So some examples of types of buoyancy problems that we would encounter in our professional life is presented here. A submarine is a good example. A boat is or a ship is something that most of the people that are living in coastal areas they are familiar with, including many people in Florida. Some of the offshore platforms, they are also anchored down to anchor blocks depending on the depth of the water. And for that type of problem, of course, we need to make sure and that we look at we treat it as a buoyancy problem. And of course, those type of problems are more complicated because then we have to consider waves and we treat them as dynamic problem rather than static problem. But the principles is based on our discussion that we have today. So our lecture objectives is to look at analysis methods and look at some equations for the buoyant forces. We are going to use the principles of static equilibrium to solve for the forces involved in buoyancy problems. We are going to take a look at some different cases and we analyze those, and we would define some conditions that must be met for the body to be stable when completely submerged in a fluid. So we're going to take a look at these four objectives. So for a body in a fluid, any type of an object or body in fluid, whether floating or submerged, it is pushed up or buoyed up by a force equal to the weight of the displaced fluid. Very important to understand that definition. It's going to help you a lot when we try to solve some of these problems. So the buoyant force acts vertically upward. It acts through the centroid of the displaced volume. If we have an object as shown here and it displaces, let's assume it's in the form of a cube and it displaces the volume equivalent to the volume of the cube, then we can mathematically define the buoyant force as density multiplied by volume. In this case, we would like to calculate the buoyant force. The buoyant force would be the density of the fluid multiplied by the volume, by the volume of the fluid that it displaces. So it's important for us to understand. F sub B in this case is buoyant force, gamma specific weight of the fluid, and V sub D is displaced volume of the fluid. Then we are going to take the principles of static equilibrium, summation of forces in the direction under consideration. In this case, in most cases of buoyancy, they're vertical. So we take the summation of that forces in the vertical direction. We set that to 0, and then we solve the problem. An example problem is given here. There is a cube 0.5 meter on a side. It's made of bronze having a specific weight of 86.9 kilonewton per cubic meter. We're going to determine the magnitude and direction of the force required to hold the cube in equilibrium completely submerged. Two cases, case A in water, case B in mercury with a given specific gravity of 13.54. One must realize here that we are, for all of the problems involving buoyancy, we would draw the two-dimensional free body diagram as shown here on the right-hand side figure, and I just put a red check mark right next to it. In such a case, when we define of course, the direction of the forces is extremely important. The coordinate system in which we pretty much define here is very important. In most cases, we assume upward direction as positive, and we base our analysis on that. If any force, any unknown after we calculate them turn out to have a negative sign, that means the original assumption that we made for the direction of the force is incorrect, and we would go ahead and change that on the free body diagram. One must be very careful to stay consistent throughout the calculation with the sign convention that we agreed upon. So we assume that the cube of bronze is submerged in water. Remember that because we don't know if it would automatically get submerged under its own aid, or if it could submerge under its own weight. We assume there is a force of F sub E, and we call that an external supporting force. If that turn, after we go through our calculations, if that force turn out to be 0, then we do not require any external supporting force. Otherwise, we need to have some kind of a supporting force. If I tell you that we have a piece of steel and I drop that in water, most of you would tell me that it's going to submerge. But there are cases in which we need to use the principles of engineering without knowing if that object would submerge or it floats. So we need to determine that. So the assumption is we assume that there are some external forces that's required. We do the calculations. If that external forces turn out to be 0, then we really don't need to have that external supporting force, and the object would be submerged in water. There are also other principles that I'm going to get into shortly. So the objective is to find the magnitude of all the forces. And of course, you're going to start with the weight of the object. All of these forces, they go through the center of the volume. So we need to determine W, F sub B, and F sub E according to the terms that I just defined. So let's take a look at the free body diagram that's shown here. Okay. Ignore all these steps that I put here, step 1, 2, and 3. Those are to be able for you to follow the book, but you really don't need to know about these steps. Just follow the steps that I'm giving you here. So we have a problem like this. Of course, we need to identify the forces, and first thing we do is we are going to write the equation of equilibrium. As such, we assume that the upward direction is positive, as I mentioned previously. So all the forces that are acting in that direction would have a positive sign, and forces that are acting opposite would have a negative sign. Or we can forget about that and have an equation with two sides. One side of the equation we're going to put all the forces with positive sign, and on the other side of the equation, we're going to put all the forces with the opposite sign, and then we would go through our calculations and solve the equations and what have you. So summation of forces in the vertical direction, we call that V is 0. As such, assuming the upward is positive, F sub B plus F sub E minus W should be 0. And from that, we know F sub E should be W minus F sub B, right? So the first thing is how are we going to calculate the weight of the cube W? It's really not that complicated. I'm sure many of you guys have guessed it. So W is nothing but gamma sub B times V, and gamma sub B is the specific weight of the bronze cube. In this case, V is its total volume. We know the cube dimensions are 0.5 meter on each side. The volume is 0.5 to the power 3. Remember, we're dealing with a cube, so we take that to the power 3, and the volume would be 0.125 cubic meter. Next, we are going to use this volume and multiply it by the specific weight of the bronze, and from there we calculate the W. Remember, we've done example problems in which we calculate W knowing the volume and the specific weight, or of course density. In this case, called W sub B, the specific weight of the bronze. So what happens is, in this case, is that the 86.9 is the kilonewton per cubic meter. Remember that specific weight would actually define weight per unit volume. So it's Newton or kilonewton per cubic meter. Multiply that by 0.125, which is the volume of the cube, and the W would be 10.86 kilonewtons. So that's a pretty heavy object, 10.86 kilonewton. So of course we need to calculate F sub B and F sub E. So F sub B is gamma sub F times the displaced volume. In this case, for water, it's going to be 9.81 multiplied by the displaced volume, which is the volume of the bronze cube. In this case, F sub B would be 120 kilonewtons. Now we know W, we know F sub B, using the equation of equilibrium that we just looked at, summation of forces in the V, set that to 0. In that case, we just calculate that how we can calculate F sub E. We use this equation. We already calculated this equation. F sub E is W minus F sub B, which is 10.86 kilonewton minus 1.23 kilonewton, which is going to be 9.63 kilonewton. And the result is positive, implying that the original direction that we assumed for F sub B was correct. If it turned out to be that this number is a negative number, then we need to go back and change the magnitude or direction of F sub E, keeping the same magnitude. So the magnitude would be the same, except we are going to change the direction. So our assumed direction for F sub E was correct. Solution to the problem is that an upward force of 9.63 kilonewton is required to hold the block of bronze in equilibrium under water. So for the second part of the problem, we would look at the cube that we just looked at, except this time it's going to be submerged in mercury. Remember, the first case it was subjected to it was submerged in water. Second case it's going to be mercury. So our objective is the same as before, to determine the magnitude and direction of the force required to hold the cube in equilibrium. Okay, so let's move on with the problem, if I can get it moving forward. Okay, so we're going to draw the free body diagram. It's going to be pretty much the same. It's pretty identical to what it is exactly the same, the free body diagram, as the previous problem. So in this case, both of the free body diagram that are shown here is correct. Note the direction that I was just referred to later, but previously F sub E. We can assume F sub B acting upward. We can assume F sub B acting downward. Both is correct. But we need to pretty much come up with a direction and assume that as our positive direction. And that's how we do it for this particular problem. So we can solve the equation as F sub B plus F sub E minus W set that to 0, or F sub B minus F sub E minus W is 0, and solve for F sub E. If it turn out to be that the direction, the sign is negative, that means the original direction was not correct, and we need to go ahead and change that. So we have now F sub E, W minus F sub B, or F sub B minus W. Let's calculate the weight of the cube. First, 86.9, that's the brass, the SG of brass. Then this is the volume, 0.125 cubic meter. We already calculated that, and that will be W 10.86. The weight of the object, unless we change the material, remains constant, whether you submerge it in water, mercury, what have you. Okay? So don't get confused. Some of you guys that may not think in engineering terms, I've heard this, that it is lighter, for example, and the object is lighter in water. Well, it's not really lighter. It has the same weight. It's the buoyancy force that make it, it's the buoyancy force that push it upward and make it feel it's lighter. The weight is exactly the same. The weight of an object on Earth is the same, whether you submerge it in water, whether you submerge it in whatever. So for the buoyant force F sub B, we need to calculate the specific, we need to get the specific gravity of mercury first, and that's a given quantity. So then we multiply that by 9.81 kilonewton per cubic meter. That's what, for water, right? And then we multiply that by volume. So we are going to calculate the specific gravity, and remember, we always calculate it by 9.81 if we are dealing in metric systems. So the subscript M refers to mercury, 13.54, and multiply, this is the specific gravity of mercury that's given, 13.54 multiplied by 9.81 multiplied by the volume, 0.125, and F sub B would be 16.6 kilonewton. Now we have W, we have F sub B, and we can back substitute to the original equation and calculate F sub E. Again, I'm going to demonstrate both ways here. F sub B is W minus F sub B, or F sub B is F sub B minus W. In this case, it's W. Please make a note of these equations and note the differences. So in this case, the final answer is 5.74. That's the magnitude of the final answer. But the direction for the first case is negative. That means that the negative sign for the solution on the left that we originally assumed is not correct, right? Okay, so now one of the questions that comes in mind is, would it be possible from the beginning to pretty much reason that a downward force would be required instead of going through the calculations. Yes, that's a possibility depending on how much engineering intuition and how much pretty much intuition, how intuitive a person is. We're all different in nature. And so for the bronze cube, the gamma sub B would be 86.9, and we could calculate that for the fluid, for the mercury. And we see that the gamma of the object and the gamma of the fluid that this object is submerged in or submerged under, there are differences between the two. In this case, we see that the gamma of mercury is much higher than the gamma of the bronze, the object. What does that tell us? That would tell us that every time we have an object as such, and if you want to determine if it would actually submerge or not, as it is shown here, we would look at the specific weight, because the specific weight of the cube in this case is less than that of the mercury. It would tend to float without an external force, and we don't need to keep it submerged with an external force, and it has a tendency to do that. Of course, in many cases we have an external force, but we can't change that. It could be the weight of something. It could be a boat that is loaded. The load itself would be the F sub E, and we want to make sure that it doesn't submerge. That's actually the way we calculate the capacity of many of the boats. And every boat it has a capacity, and if you overload it, that external F sub E would be higher than it should be. In some cases, it should be 0. So as such, we would put the boat itself or the ship itself at the risk of submerging under water. Let's take a look at another problem. A cube of 80 millimeter on each side is made of a rigid foam material and floats in water partially. In this case, 60 millimeter of the cube would be below the surface, and 20 millimeter would be above the surface. We calculate the magnitude and direction of the force required to hold it completely submerged in glycerin with the specific gravity of 1.26. So first, again, we follow the same principle. First, we need to calculate the weight of the cube, and then we would calculate F sub E, or the force required to hold the cube submerged. Again, we're going to use the free body diagrams in the below image. A cube floating on water, and B, a cube submerged in glycerin for the two cases that we are looking at. First, we are going to use the principles of equilibrium, summation of forces. In the vertical direction, we set that to 0. We assume F sub B, in this case, upward is positive. So we assume this direction to be positive. F sub B is positive upward. W is acting downward, that's negative. W would be F sub B, would be gamma times B sub D. B sub D, we can simply calculate that, but we need to be careful with one thing here, though. You need to calculate the submerged volume of cube for the first case, not the total, because we're only dealing with the portion that is submerged, not the entire cube. In that case, V sub D, or the part of the object that is submerged, is 38 point, or partially submerged, 384 times 10 to the power 3 cubic millimeter. This is for the submerged volume of cube, not for the total volume because only a portion of the cube is given as submerged. That's given in the problem. If we don't know how much of it will be submerged, then according to the buoyancy, we're going to calculate the buoyancy. We're going to calculate the gamma, and we're going to compare the two. And it is possible that we are not sure if it's partially submerged. We can do that, and then we can see that what's going to happen to F sub E, and from there we may be able to determine if it is partially submerged. So W is 9.81 times 10 to the power 3 multiplied by 384 times 10 to the power 3 cubic millimeter. We need to convert that to cubic meter. So these two would cancel out. The cubic millimeter and cubic millimeter here is going to cancel out. 10 to the power 3 here and 10 to the power 3 here. Of course, we want to make sure that we do this right. Okay, this is 10 to the power 3 to the power 3. Okay, that's 10 to the power 9. So W would be 3.77 Newton as the weight of the object. Then, knowing W, we set the summation of forces in the V. This is for part A. So as such, F sub B would be a W. So F sub B would be 3.77, right? That'd be F sub B. Then so in order to calculate F sub E, in this case, we need to follow the principles of equilibrium. Summation of forces in a vertical direction is 0. F sub B minus F sub E minus W, we set that to 0. F sub E is F sub B minus W. Gamma sub F V sub D minus 3.77. We already calculated this from previous step. V sub D in this case would be the total volume of the cube, because we assume it is not partially but completely submerged. So we calculate that by knowing that each side is 80 millimeter long, and this is a cube. You take that to the power 3. So it's going to be cubic millimeter as it's shown here. Remember, in previous steps, we only calculate the volume of the submerged portion of the cube. Gamma sub F, we can easily calculate that. F sub E is then gamma sub F multiplied by V sub D. And then we subtract W from that, which is gamma sub F V sub D minus 3.77 Newton. And we're going to go through the calculations. Make sure you guys understand how we convert all these dimensions, convert all the units. That's very important. And eventually F sub B would be 6.33 minus 3.77, which is 2.56. Originally, we assumed a force direction of 2.56. That is correct. A 2.56 Newton is required to hold the cube submerged in glycerin. And again, you can see the application in I keep saying ship in the marine industry, in which we need to keep something submerged, or we need to keep something partially submerged or completely submerged. We want to make sure that we, it all works according to the principles that we are discussing today. There's really no magic to this. That's the beauty of engineering. Engineering is logic, and it is based on principles, and you can never go wrong with engineering. You can never go wrong with, I should say, correct engineering, because sometimes I look at some of these websites and there are a lot of information. There are many credible websites out there, but one must be careful with some of those websites. Some of the problems there, they may include errors. So when you're referring to some of the websites, be careful, always check the numbers, make sure they do their calculations correct. That brings me to the end of the slides for today's discussion. If you have any questions, make sure to send them to me via the course website. I hope you find these discussions that take such a long time to prepare useful for your study. Thank you.